Okay, so before we continue with harmonic manifolds, I just want to give some motivation for harmonic functions in terms of the what's called the Dirichlet energy of maps, since Utsav was interested in this. So suppose D is a precompact domain with smooth boundary. In an oriented Riemannian manifold N, so if we take a function u, let's say, which is smooth on the domain D and continuous on the closure of D. Okay. Well, okay, let me take it actually to be smooth on a neighborhood of D. So smooth on the closure of D means that the partial derivatives extend continuously to D closure. Okay. So then we can define its Dirichlet energy. E of u is half the integral over D of norm grad u squared d vol. Okay. So the name energy is motivated by the fact that if you think of u as a potential function, then say gravitational or electric potential, then particles will move under the gradient flow. So that means the flow of the vector field grad u. And so the velocity of the particles is given by grad u. So this norm grad u squared, this is the speed squared, right? So half the speed squared, if the particles have unit mass, this is half mv squared. So that's the kinetic energy. And you're integrating over the domain to get the total energy. All right. Now, we could try and minimize. So the problem proposed by Dirichlet was to, given a continuous function on the boundary, so given f a continuous function on the boundary, okay, minimize the energy over the set. So let me call it C, C sub F, which is yeah, okay. Actually, well, let me okay, let me stick to this. Smooth on D and continuous on the closure is, so then this energy a priori may be infinite, but we'll be looking at finite energy maps, finite energy functions. So you take u in C infinity D intersect C0 D closure such that U restricted to boundary D is equal to F. Okay. Okay, so this means that if you think of U as, for example, temperature, so that's that gives a potential function. Then you're fixing the temperature on the boundary of your domain, and then you're looking at the least energy configuration subject to these boundary conditions. Okay, so you want to minimize the energy subject to the boundary values fixed equal to F. Okay, so if you want to minimize, suppose there is a minimizer. Okay, so Riemann argued that, by physical intuition, it was just a intuitive argument that you allow heat to diffuse into the domain. You keep the boundary of the domain, the temperature of the boundary fixed. You allow heat to diffuse, and then the system will assume a minimum as time tends to infinity. The system will converge to a least energy configuration. Okay, so there will exist a minimizer. Later, this was actually shown to be false without some false in general. So anyway, so suppose we do have a minimizer, then we can differentiate the energy at that minimizer and see what happens, right? So suppose we have a one parameter family. So suppose U naught in this CF minimizes the energy. Yeah. Then you take a one parameter family of functions, UT, so that UT belongs to this set of functions with boundary values F. Okay. And we assume this one parameter family is differentiable in T. So we define a function V of X. This is the variation. This is ddt at T equal to 0 of ut of X. Okay. So this is smooth on D. And because the UT's, their boundary value is constant equal to F, that means that the derivative at the boundary will be 0, right? So V restricted to boundary D is 0. Okay. Now you look at then the derivative of the energy. So since we're assuming that U naught is a minimizer of the energy, the derivative of the energy is 0. Okay. Now, what is this energy? It's half the integral over D of inner product grad U, right? D vol. So if I take the energy of UT, so I'll have inner product of grad UT, and I'm differentiating with respect to T, right? So what will I get? I'll get 2 times the inner product of ddt of grad UT, inner product grad UT at T equal to 0. And ddt of grad UT this will be the gradient of my function v, right? Okay. So I'll get a 2 here, which cancels with the half. So this is going to become integral over d in a product of grad v with grad u, right? D vol. Yes, is this okay?
Yes, sir.
Now we can do an integration by parts here. So we use the formula that we proved for the divergence of a function times a vector field, right? This was phi divergence x plus inner product grad phi x, right? Yes. So if we put phi equal to v and x equal to grad u, then we get that the divergence of v grad u is equal to v times the divergence of grad u, that will be Laplacian u, plus inner product grad v grad u, right? Okay. So this inner product grad v grad u, I can write as a divergence minus v Laplacian u. So this becomes integral over d divergence v grad u minus inner product, minus v Laplacian u minus v Laplacian u d vol. So this is minus inner product v Laplacian u d vol, plus by the divergence theorem, this is the second integral is the integral over boundary d of inner product of v grad u with the normal vector ds, but v is 0 on the boundary of the domain d, right? So this is 0 on boundary d. So this second integral vanishes, right? So the boundary term vanishes. So after this integration by parts, you get just minus integral over d v Laplacian u d vol. Is this all right? Yeah.
Yes, sir.
So therefore, if this derivative of the energy is 0 for all variations, that means for all v, you can take v to be, you can start with a function v and you can define a variation ut whose variational function is equal to v, right? So now what you can do is, given, let's say, v in cc infinity of d, you just let ut of x be the function ux plus tvx, right? Just take a linear variation, right? Okay, so this will also have the same boundary values, right?
Yes.
And so we get this integral is 0 for all v with in cc infinity d. So therefore, this implies that Laplacian u is 0, right? Okay. Okay, so we get that the Laplace equation, Laplacian of u equal to 0, this is actually the Euler-Lagrange equation for the Dirichlet energy, right?
Yes.
Okay, this is the Euler-Lagrange equation for the Dirichlet energy. So a minimizer of the energy, therefore, should be harmonic. All right. So this is one motivation for harmonic functions. And this computation, not only does it tell you that a minimizer should be harmonic, it also suggests a way to find a minimizer. Namely, what have we computed? We've computed the derivative of the energy along a variation in the direction of the function v. So if you think of the energy function, okay, as a function on an infinite dimensional space, all right, so this CF to R, okay, then what we've computed is that the derivative of the energy function at a point U applied to a tangent vector V. So V is a function also. You think of V as a tangent vector to CF, right? This is equal to minus the integral over D of V Laplacian U d vol, which is equal to minus the L2 inner product between V and Laplacian U, right? Right?
Yes.
Okay. So what does this mean? This means that if you think of the energy function as a function on an infinite dimensional space, equipped with the L2 inner product, then in other words, what this means is that the gradient of the energy function at U is equal to minus the Laplacian of U. Okay. Does this make sense, right? Yeah, remember how gradient is defined, right? The derivative acting on a vector is defined, the gradient vector field is defined by the property that the derivative acting on a tangent vector is given by inner product of the gradient with the vector, right? So here we are getting inner product of the tangent vector V with the gradient, with this vector Laplacian U, right? So therefore, by definition, the Laplacian minus Laplacian U is the gradient of the energy function. Does this make sense?
Yes, sir.
Okay. Yeah. So now what do you want? Do you want, so you have this infinite dimensional space, which maybe looks something like this. This is your, this space is CF, this infinite dimensional space. And what do you want? You want basically the minimizer, right? This is the minimizer U naught. This is the minimizer of the energy. So how would you find a minimizer of the energy function? You take the gradient, the minus the gradient flow, right? That's how that should converge to a minimizer, right?
Yes.
So you take the flow of minus grad E, right? Now what is minus grad E? Minus grad E is the Laplacian, right? Okay. So therefore, what will the gradient flow be? Gradient flow of minus the energy. This is the flow that will converge to the minimum of the energy, right? The gradient flow of minus the energy. That means that del T of ut should be equal to minus grad E of ut. That should be equal to Laplacian of ut, right? Okay. Right? Yes.
Yes, sir.
So what is this? This is the heat equation. This is the heat equation. In other words, the heat equation is equal to the gradient flow of minus the energy. Does this make sense?
Yes.
Okay. So this is why you would expect the heat flow to converge to a harmonic function. Okay. Because under the heat equation, the energy should decrease, right? And it should keep decreasing until you reach the minimum. This is the heuristic idea. Why the heat flow. And this one can prove that actually if you take a solution of the heat equation with fixed boundary conditions, F, then it will converge to the if the boundary of the domain is nice, a smooth boundary, then it will converge to the unique harmonic function with those boundary values, which will be the minimum energy function. Okay.
Yes.
All right. So you can already see that the energy is going to be monotonically decreasing along the heat flow, right? Because what will the derivative of the energy be? Along the gradient flow, ddt of, along the heat flow, ddt of the energy of ut, right? What will this be? This will be the inner product of the gradient of the energy, grad E ut, with ddt of ut, right? And ddt of ut is minus the gradient of E. So this will be minus the gradient E ut. Okay. So this will be minus the norm of grad E ut squared, and that is minus the L2 norm of Laplacian ut. Okay. All right. So you see the energy is monotonically decreasing along the flow. Is this clear?
Yes.
Yes, sir.
Yeah, Rudrada, is this okay?
Yes.
So this is motivation for the heat equation, where you see it as an infinite dimensional gradient flow, right? You see it as an infinite dimensional gradient flow. So motivation for the heat equation. Yeah. So this same motivation will later work for harmonic maps. This is for Utshab. You see, there's a heat flow for harmonic maps where, again, it arises as the gradient flow of minus the energy. You can define the energy of a map similarly to the energy of a function, and then the gradient flow of minus the energy leads to a harmonic heat flow, a harmonic maps heat flow. So,
Yes, yes.
yeah, I just wanted to give this motivation. Okay. So,
Yeah. Thank you, sir.
So you see, the thing is, the energy controls to some extent, it gives an equicontinuity of the solutions to the heat equation, because this L2 norm of, this is a Sobolev norm essentially, right? This energy.
Yes, yes.
So if you know that you're bounded in Sobolev norm, then you will get some from that, from the Sobolev inequalities, you'll get some equicontinuity of the functions. You see?
Yes, yes, yes. Right.
That's the idea. So from that, from the boundedness of the energy is monotone decreasing, it's going to be bounded. So from the boundedness of the energies, you can get an equicontinuity. From that, you can extract a convergent subsequence and, and try and prove existence of a limit. Okay, that's the idea. To
Yes.
prove
Yes.
existence of a limit. Okay. Because, So the boundedness of the energy gives you, so it uses what's called the Poincare inequality. So the Poincare inequality estimates the change in the function in terms of L2 norms of its derivative. Okay.
Yes. Yes. Yes.
So the Poincare inequality will give you an equicontinuity. And a similar idea is used for maps, for the harmonic map heat flow. When the curvature of the target manifold is non-positive, you'll get a monotonicity of the energy. And from that, you can prove convergence. That's the idea behind Eel-Sampson's theorem. Okay.
Okay. So
Yes.
here we're using the Poincare inequality in the way that, like, the Poincare inequality says that the LP norm of the function will be dominated by the gradient, the LP norm of the gradient. So here the energy is precisely given by the gradient, so we get the equivalent, that boundedness using that. That's what you're
We
saying.
get the boundedness.
Yeah.
Yeah.
Okay.
Yeah. That's the idea. Okay, so anyway, I just wanted to make this remark that this is some motivation for harmonic functions and for the Dirichlet problem, right? So, I mean, this was Riemann's argument for saying that a solution to the Dirichlet problem exists. He just said, look, by physical intuition, you will have a minimizer of the energy because the system, a physical system, will evolve till it reaches equilibrium. Okay. And what he meant by the evolution was exactly the heat equation. Right, the physical system evolves according to the heat equation. Okay. So, yeah, that's okay. So fine. So yeah. So we'll be talking extensively about the Dirichlet problem in the next few classes. So this was just some motivation for that. Okay. So now we can come back to harmonic manifolds. So on a harmonic manifold, last time we stated this mean value property for any harmonic function, right? So if U is harmonic in a neighborhood of a closed ball with center P and radius R, then the value of U at the center of the ball is equal to the mean value of U over the sphere of radius R. So the mean value over the sphere means the integral over the sphere with respect to surface area measure of the sphere divided by the total surface area of the sphere. And that integral we saw last time, that is the same as this integral, right? Over the unit tangent sphere at P, U of X RV, d lambda P of V, where d lambda P is the usual Lebesgue measure on the unit sphere, right? On the unit tangent sphere. Okay. All right. Yeah. Into 1 over the area of the unit sphere. Okay. So how do we prove this? So the idea is to look at this function. H of Q is the Green's function G sub P of Q minus G sub P of R. Okay. So what properties does this function satisfy? H is harmonic on the manifold minus the point P, and H restricted to the boundary of P is or the boundary of the ball is 0, right? Because I'm subtracting the value of G of GP at R, right? Okay. Yes.
Yes, sir.
Okay. And so this function, if I look at, so I have my ball. This is center P and radius R. And I'm taking H of Q is GPQ minus g of r. G here was the function on the real line on, where g composed with the distance function dp is equal to gp, right? Here, gp is equal to g composed with dp. Okay. Here, g prime was minus 1 over cn, 1 over j, where j was the Jacobian, right? Okay. And so H satisfies the following properties. Laplacian of H, in the sense of distributions, this will be minus the Dirac at P, right? And H restricted to boundary of the ball is 0, right? Yeah. So these two properties, these are actually uniquely characterize H. Okay, because later we'll prove the maximum principle for harmonic functions, right? So if I have two such functions which satisfy these two properties, that the Laplacian is minus the Dirac and H restricted to boundary B is 0, right? If I have two such functions on the ball B, say H1 and H2, if I look at H1 minus H2, then the Laplacian of that will be 0 and H1 minus H2 will be 0 on the boundary. So H1 minus H2 will be harmonic on the whole ball and 0 on the boundary. Therefore, by the maximum principle, it will be 0, right? Okay. So there is a unique such function which satisfies these two properties. So this function is called the Green's function for the ball with pole at P. This is the Green's function for the ball B with pole at P. Okay. So using the Green's function for the ball with pole at P, we can get a representation formula for any harmonic function in the ball. We can find its value at P. So that follows formally from Green's formula, right? So if I just formally plug in Green's formula, if U is harmonic on B, then what does Green's formula say? It says the integral over D of U Laplacian H minus H Laplacian U dvol is equal to the integral over boundary D. So integral over the ball B, integral over boundary B of U inner product grad H n minus H inner product grad U n ds, right? Now, if I just formally compute, then this Laplacian H will be minus the Dirac, right? So U times minus the Dirac, that integral should be this first integral here. This should give me minus U of P, right? Yes?
Yes.
Okay, by definition of the Dirac, right? So, and this second integral will vanish because U is harmonic. Okay, so the left-hand side becomes just minus u of p. And what happens to the right-hand side? Well, h is 0 on the boundary, right? So this second term vanishes and just this first term remains, right? So you get this green representation formula for any harmonic function, okay, that minus u of p is the integral over the boundary of the ball of u into this inner product of grad h n. This is normally written as del h del n, okay, the normal derivative of the Green's function. Okay. All right.
Yeah.
Okay. So this gives a representation. So you see, all we used was formally was this fact that the Laplacian of h is minus the Dirac at p, and h is 0 on the boundary of the ball, right? So here p, I mean, we could have done this if p was any other point in the ball, right? Then we would have got a formula for the value of u at any point in the ball, right? Okay.
Yeah.
So maybe I should call this h sub p, okay? Because yeah, so h sub p. So this tells us that harmonic functions, they should be representable in terms of their boundary values by integrating with respect to the normal derivative of the Green's function with pole at the point P. All right. Okay. Now the problem is, of course, that we have to justify this computation. This was just a formal computation. So the problem is that this H has a singularity at P, right? So what do? Well, we do the usual thing. We cut out a small neighborhood around P. So we cut out a ball around P of radius epsilon. Then H is smooth in this annulus. And then we apply Green's formula to this annulus. Okay. So that's what we're going to do. All right. And then let epsilon tend to 0. Okay. Yeah. So that will justify this formal computation. Okay, so let's start a new session and then we'll do this proof. Okay. Oh, so now let's prove this mean value property. So we've defined this function h, which vanishes on the boundary of the ball. So now we define this domain d epsilon is the large ball of radius capital R minus the closed ball of radius small epsilon. And then we apply Green's formula to the domain d epsilon. Okay. So then this integral h Laplacian u minus u Laplacian h, this will become 0 over the domain d epsilon because both Laplacian u and Laplacian h are 0 on the domain d epsilon. Okay. On the other hand, by Green's formula, this is the integral over the boundary of this domain. So there we'll get two terms. The boundary of this annulus, there's a sphere of radius r minus the integral over the sphere of radius epsilon, right? So when we integrate over the sphere of radius r, there is one term which is h into inner product grad u n, right? But h is 0 on the boundary of the sphere of radius r. So that term vanishes, okay? So we'll get just minus u times integral inner product of grad h with n, okay, d sigma r, minus the integral over the boundary of the ball of radius epsilon, h grad u n minus u grad h n d sigma epsilon. And now this first integral, this grad h n, this is the radial derivative of the function h, right? This is the derivative in the radial direction perpendicular to the sphere. So that will be just h is equal to the Green's function minus a constant. So this is the same as the radial derivative of the Green's function, right? And what is the radial derivative of the Green's function? It is just this G prime, right? And G prime is minus 1 over this constant Cn into 1 over J, all right? So this term here, this will become, there's a minus sign, and then I'll have another minus sign, and then I'll have a 1 over Cn, and then I'll have 1 over the Jacobian, right? Okay. And then this U, I make a change of variables. The integral over the sphere of radius r, I make a change of variables. It becomes an integral over the unit sphere, and I get U of x rv, and then this 1 over jr, and then into jr d lambda p, right? Okay. Yes, is that all right?
Yes.
Okay. And then I have this other integral over the sphere of radius epsilon, u inner product of the gradient of the Green's function with n minus h grad u n. Okay. So this 1 over jr and the jr cancel. I get 0 equal to, this is the mean value which I wanted, right? This is the mean value over the sphere of radius r. And then I have these other two terms. Okay. And this this first term here, u into inner product of grad gp with n, integral d sigma, this we already saw, this converges to minus up, right? By a previous lemma. Yes? Okay, we did this lemma last time, if you
Yes.
remember.
Yes.
This lemma here, right? This integral converges to minus the value of the function at p. Okay. So by that lemma, this term goes to minus up, and the second term goes to 0, because this grad u n, this is bounded, and the integral of h mod h d sigma over the sphere of radius epsilon, this goes to 0. Okay. Because h is bounded by a constant times the Green's function g, right? A constant plus the Green's mod of the Green's function. Okay. So, and the integral of the Green's function, mod of the Green's function over the sphere of radius epsilon, that we already saw, it goes to 0, right? So this last term here goes to 0. So we get finally this converges to the mean value over the sphere of radius r minus u of p. So this is equal to 0, and that proves the mean value property. Is this all right?
Yes.
Yes.
Okay. So we have the mean value property for harmonic functions on a harmonic manifold. Okay. So once we have the mean value property, then we can prove the maximum principle by the usual, the same proof as in Euclidean space. So suppose M is a harmonic manifold and U is a harmonic function on a domain D. If U attains its maximum at some point of D, then U is constant. So here domain always means open connected set. Okay, so the point is connectedness. So suppose U attains its maximum at some point P naught in D. Okay, so U of P naught is equal to the sup of U of P over P in D. So call the sup equal to M, say. So let E be the set of P and D where U attains its supremum. Okay, then because U is continuous, this set E is closed, right? And it is non-empty by hypothesis. P naught belongs to this set E. So now all we have to show is that this set is open, right? So then it's open, closed, and non-empty. So that must be all of D. And so therefore U must be constant, right? So to show it's open, we use the mean value property. So take a point P in D. Oh, I shouldn't, this is a typo. I meant to write E here. So take a point P in E here. I want to show that E is open. So I take a point P in E. So let R be positive such that BPR, again another typo, sorry. BPR is contained in the domain D. Then by the mean value property, the mean value of u over the sphere of radius little r of around P, this is equal to the value of u at P, and this is equal to the supremum M, right? So this is for all little r in between 0 and capital R. And on the other hand, for any sphere of radius little r, u is less than or equal to M. But if the mean value is equal to M, then it follows that u must be constant equal to M on the sphere of radius little r, right? Yes?
Yes.
Okay. And so this is true for all r in between 0 and r. So that means u is constant equal to M on the ball of radius capital R. Okay. Since it's constant on each sphere, and so it's constant on the whole ball. And so therefore this ball is contained in the set E. Therefore E is open and it's also closed and non-empty. So therefore E is all of the domain D. And so U is constant equal to M. All right.
Yes. So this mean value property is also equivalent characterization of harmonic manifolds, right?
Yes, that is true. That is true. I need to think about the proof of that. Yeah, that is true. It is an equivalent characterization of harmonic manifolds. Yeah. I'll have to think about that. Yeah. That is true. That is true. Yeah. Yeah, I don't know the proof of that. I don't know the proof. Okay. So as a corollary, we get, so that's the strong maximum principle. If you attain your maximum at a point in the interior of the domain, then the harmonic function is constant. And we also have the weak maximum principle for harmonic manifolds. So if D is a domain in M and U is a C2 function in the interior of the domain, which is continuous on the closure of the domain, and such that the Laplacian of U is 0 on the domain D, it's harmonic in D, and suppose D closure is compact, then the supremum of U over D closure is equal to the supremum over boundary D. The supremum of U over D closure is equal to the supremum of U over boundary D. Okay, so for the proof, let P naught be a point in D closure where U attains its maximum, its supremum, say M. So if P naught belongs to boundary D, we're done, right? Otherwise, P naught belongs to the interior of D. And so then U is constant on D by the strong maximum principle. And so therefore, by continuity, U is also constant equal to M on the boundary of the domain. And then it follows that the supremum is attained on the boundary. All right. Yes?
Yes.
Yeah, why it is called weak?
Why is it called weak? Because, well, one reason is the strong principle implies the weak, right? So,
Okay, strong is really stronger than this.
yes, strong is stronger.
Also, one reason is that here in the strong maximum principle, we are assuming the domain to be, the closure to be compact, bounded, something like that. But in the weak, we require the closure to be compact, meaning bounded.
Well, also, we're not assuming the function to extend continuously to the boundary, right?
Right.
It's defined in the interior.
Yeah, it may very well blow up at the boundary or something like that.
It could blow up at the boundary. A priori, it could blow
But
up.
for the weak, we have that extra assumption that it's also continuous up to boundary. Yeah.
Yeah. Yeah. And we don't have the stronger conclusion that the function is constant, right? So, yeah. Right. Yeah. So, yeah, I suppose that's it. Okay. So, either way, from the weak maximum principle, we can say that a harmonic function is determined by its boundary values, right? So precisely speaking, if U and V are harmonic on a domain D in a harmonic manifold such that D closure is compact, and if U, V are continuous on D closure, then if U is equal to V on the boundary of D, then U is equal to V on the domain D, right?
Right.
Yes.
Okay, so you just apply the weak maximum principle to the harmonic functions U minus V. So this will be less than or equal to 0 on the whole domain because it's 0 on the boundary. And look at also V minus U. This will also be less than or equal to 0 by the same argument. And so both are 0. And that's it. Okay. So a harmonic function is determined by its boundary values. So this motivates the following question, which is the Dirichlet problem, right? So given a domain D such that D closure is compact, and given f a continuous function on boundary D, does there exist a harmonic function which is C2 in the interior and continuous on the closure such that U restricted to boundary D is equal to f? Okay, in other words, can you extend any continuous function on the boundary to a harmonic function in the interior? Okay. So by the weak maximum principle, if a solution to the Dirichlet problem exists, then it is unique, right? So there can be at most one solution to this Dirichlet problem, if there is a solution at all.
Right.
And we've already seen another motivation for the Dirichlet problem in terms of the Dirichlet energy, right? This function, if it exists, this should be a, well, we saw that a minimizer of the Dirichlet energy should be harmonic in the domain. And then by the weak maximum principle, we've seen that the harmonic function with fixed boundary values is unique, right? So that means there should be a unique minimizer of the Dirichlet energy, right? Okay, by the weak maximum principle. Okay. So what we're going to do,
So,
we're going
sir,
to, yes, go ahead. Yeah. Yeah.
so if I have a harmonic extension of the function, then I'll have a minimizer.
Yeah, that's true. It will be the minimizer. It will be the minimizer. That is true. Yeah, that is true. Yeah. See, what one can do is, normally to show the existence of a minimizer, what you do is you take the infimum of the energy and then you take a sequence converging to the infimum of the energy. Okay. And then because the energy is bounded, you have a bounded sequence in the Sobolev space, W12, and then you have the Relic-Kontratjov theorem, which says that W12 embeds compactly into L2. So it will be, so your sequence will be pre-compact in L2. And so you'll get a sequence which converges strongly in L2. And then you can show that a subsequence which converges strongly in L2. And then you can show that the energy is semi-continuous. So the limit will also minimize the energy. And in particular, its energy will be finite. It will be in the Sobolev space. And then you can actually show convergence in the Sobolev space as well. And so you'll get a minimizer in the Sobolev space. And then because it's a minimizer, you can show that it's a weakly harmonic. Okay, so its distributional Laplacian is 0. And then by elliptic regularity, it will be actually smooth and harmonic. Okay. And so, right, so, yeah, so you have a minimizer, and then the minimizer has to be harmonic, and then by the maximum principle, that harmonic function is unique, right? So it must be the solution of the Dirichlet problem, right? So
Okay.
so
So
you,
this
you show
direction
that,
is not easy to show. This
what?
requires this that the harmonic extensions are minimizers. This is not straightforward.
Well, you show that a minimizer exists, and then the minimizer has to be harmonic, and then
Unique.
there's a unique harmonic function, right? So that proves that the solution of the Dirichlet problem is the minimizer, right?
Okay. Okay.
So you show that any minimizer is harmonic, and that's enough to conclude that
Right.
the solution, there's only one harmonic extension. So that's it. So yeah. Yeah, I mean, the only difficulty with the Sobolev space approach is in what sense the boundary function f is equal to the boundary value of the function inside. Okay, because normally for functions in the Sobolev space, you have what's called the trace theorem. There's a mapping from the Sobolev space of the interior to the Sobolev space of 1 degree lower of the boundary, which is a boundary value mapping. It's called the trace. So there's a trace theorem for Sobolev spaces. So in terms of traces, yeah, the trace of the minimizer is equal to the function f on the boundary. But that doesn't mean that actually it's a continuous extension. It doesn't mean that necessarily. So that's a bit subtle. So yeah.
Oh.
Okay. Yeah. More questions? Okay. So let's first solve the Dirichlet problem for a ball in Rn. Okay. So now recall that the Jacobian of Rn is given by J of R is equal to just R to the n minus 1, right? We've seen this already. Yeah. So therefore, the Green's function is going to be given by integrating 1 over j, right? And so when n is equal to 2, we get that the Green's function with pole at x is 1 over c2 into log of 1 over norm x minus y. Here, this constant Cn, as always, is the volume of the unit sphere in Rn. And in higher dimensions, the Green's function is 1 over Cn into 1 over n minus 2, 1 over norm x minus y to the n minus 2. All right? Okay. So what we want to do is we want to construct a Green's function for a ball in Rn. All right. So we have a ball in Rn. And we have a point in, so here's, let's say it's the center of the ball is the origin in Rn. And I have a point P. Okay. We want to construct this function H sub P, right? So we have a point P in a ball B. Let's say the unit ball B01. And we want H sub P such that the Laplacian of H sub P is minus the Dirac at P, and H sub P restricted to the boundary of the ball is 0. Okay. So if we take the Green's function with pole at P, the problem is it's not 0 on the boundary of the ball, right? Okay. So what we want to do is subtract some appropriate function to get a harmonic function inside with a pole at P, which is 0 on the boundary of the ball. Okay. So the way to do this is by using reflection in the unit sphere. Okay. So here's P, and reflection in the unit sphere means you extend this radius to a point P star such that the product of these two distances, P times P star, is equal to 1. Okay. So if we were doing this in 2 dimensions, then this map P goes to P star. This is just Z goes to 1 over Z bar, right? Okay. This is just Z goes to 1 over Z bar. This reflection in the unit circle. Yes. Right. Now, reflection in the unit circle is anti-holomorphic, right? If Z goes to 1 over Z bar, it is anti-holomorphic. Yeah, it's the conjugate of a holomorphic function.
Yes.
And if I take the Green's function with pole at P, if I compose it with this reflection, right, then that will also be harmonic, right? Because a harmonic function composed with an anti-holomorphic function, that will also be harmonic, right? Because a harmonic function is locally, it's the real part of a holomorphic function, right? So what if I take a harmonic function composed with anti-holomorphic, what will that be? That will be real part of holomorphic composed with anti-holomorphic. Now, holomorphic composed with anti-holomorphic is anti-holomorphic, right? And so I get real part of an anti-holomorphic function that is harmonic, right? Yeah, the real and imaginary parts of an anti-holomorphic function are also harmonic. So the Green's function composed with this reflection in the unit sphere, that will be a harmonic function with a pole at P star. Okay. But the point is, when I take the difference of these two, what will happen is I'll get a harmonic function which will vanish on the boundary. Okay. I'll get a, because on the boundary P is equal to P star, right? So here I'll just get G of P minus G of P. They'll cancel. So I'll get 0 on the boundary. Does it make sense?
Yes.
Okay. So that's the idea. That's how you can, in 2 dimensions, that's how you can construct the Green's function with pole at P. Okay. You look at basically GP of Z minus GP of 1 over Z bar. 1 over Z bar. I think this should work. Let me just check. Yeah, so see, where is this going to be? This GP of 1 over Z bar, where does this have a singularity? This has a singularity when 1 over Z bar is equal to P, right? That means that Z is equal to P star, right? Z is equal to 1 over P bar. So that is outside the unit disk. So this is harmonic inside the unit disk, right? Okay. This has singularity. This has a pole at P star equal to 1 over P bar, which is outside the unit disk. Okay, so this is good inside the unit disk. So when I take the difference, right, this is going to vanish on the boundary because on the boundary, Z is equal to 1 over Z bar. So these two will cancel, right? Okay. So this is my function HP of Z. This will satisfy these two properties, right? Okay. So here I'm taking the Laplacian restricted to the ball. Inside the ball, the Laplacian is minus the Dirac. Okay. Is this clear? Yeah, this was what we would do in 2 dimensions. Yeah.
Yes.
Okay, and then once we have this H, then I just apply Green's formula, you see, and I'll get this representation formula that minus U of P is the integral over the boundary U times the normal derivative of the Green's function with pole at P. Okay. Yeah, so that will give me this will actually give me the Poisson formula. Poisson integral formula for the representation of harmonic functions in the ball. Okay. So we're going to do this actually in any dimension. So we're going to do this in any dimension. So in any Rn, we let x star, this is going to be the reflection in the unit ball, in the unit sphere. This is x over norm x squared. Okay. So then the norm of x star is 1 over the norm of x. And now we do a computation that if xi is a point on the unit sphere Sn minus 1, let's look at the norm of x star minus xi whole squared. So x star, I substitute the formula for x star. It's x over norm x squared. And I write this norm squared as inner product with itself. And then I use bilinearity of the inner product. So when I expand, what am I going to get? I'm going to get 1 over norm x squared minus 2 inner product xi over norm x squared plus 1, right? Because norm xi squared is 1. Okay. And now I take a 1 over norm x squared common. So then I'll get 1 minus 2 inner product xi plus norm x squared. This thing over here, this I can write as norm of x minus xi whole squared, right? Okay. Okay, so I get this formula. So what does that mean? That means norm of x star minus xi whole squared is norm x minus xi whole squared divided by norm x squared. So I cross multiply. And so then I get that norm of x minus xi is norm x into norm x star minus xi. Okay, where x is in Rn minus 0 and xi is in Sn minus 1. So if I look at the Green's function with pole at x applied to a point on the unit sphere xi, right? So this is going to be my function on R, G applied to norm of x minus xi, right? Yeah. And that is equal to G of norm x into norm x star minus xi. Okay. So then this is when xi is on the unit sphere. So this function that I get here of xi, this is for xi on the unit sphere. Now I define the same function for y in Rn, except in Rn minus the point x star. So I define hx of y is g of norm x into norm x star minus y. Okay. So then because scalings in Rn, they preserve harmonicity. This function h sub x, this is going to be harmonic in the complement of x star, right? Okay, this has a pole where, I mean, G has a pole at 0, right? So this is going to have a pole when y is equal to x star, right? Otherwise, it's going to be smooth, okay? So this is going to be harmonic in Rn minus x star. Okay, so this is going to be a harmonic function with a pole at the reflected point, x star. Okay, so that means in particular, this function hx is going to be harmonic in a neighborhood of the unit ball, right? And what is the point of defining this function? The point is this function, it equals the Green's function g sub x, right? When xi is on the boundary of the ball. That's why we define this in this way, right? G sub x of xi is also equal to h sub x of xi, right? when xi is on the unit sphere, right? These two harmonic functions, they agree on the unit sphere. Therefore, if we define g sub x hat of y to be gxy minus hxy, then we would have constructed the Green's function for the unit ball. That is, so this g sub x hat, this is harmonic on a ball containing the unit ball. So on B0 r minus singleton x for some r bigger than 1, okay, depending on x. This is 0 on the boundary of the ball, because on the boundary of the ball, gx is equal to hx. So these cancel, okay. And gx hat is equal to gx plus big O of 1 in a neighborhood of x, in a punctured neighborhood of x, because this hx is smooth near x, right? This has a singularity outside the ball. So inside the ball, this is smooth near x. And the gradient of gx hat is equal again to the gradient of gxx, gradient of gx plus something bounded, okay? All right. So this function gx hat, this will be the Green's function of the ball with pole at x, all right? And for x equal to the center of the ball, there we just did what we did for our, in the proof of the mean value theorem. We take g naught hat to be g naught y minus g naught 1, all right? Just minus a constant, okay? Is this all right? Yeah. So here's the picture. We have the unit ball. We have a point x. And we have the point x star, the reflected point. And I have my function g sub x of y. This is g of norm x minus y. Okay. And when y is equal to a point on the boundary of the ball, right? This is g of norm x minus xi. Then this becomes equal to g of norm x into norm x star minus xi. Okay. And this I write as hx of xi. Okay. Where hx of y is the function g of norm x into norm x star minus y. All right, makes sense? Yeah. Okay, so gx has a pole at x and hx has a pole at x star. Okay, and they agree on the boundary of the ball. So when I subtract, I get a function which inside the ball only has a pole at x and vanishes on the boundary of the ball. All right. Yeah, that's my function gx hat. That's the Green's function for the ball. It vanishes on the boundary of the ball. So it's gx minus hx. Okay. So this is smooth on the ball minus x. Okay. right? Is this all right? Gx hat
Yes.
restricted to the boundary of the ball is 0. Okay, fine. So we've got our Green's function for the ball. Now we can prove a Poisson formula. So suppose for simplicity, U is harmonic on a neighborhood of the closed ball. Okay. Then for X in the boundary of the inside the ball, we apply Green's formula to the harmonic functions U and Gx hat. Okay, on the domain d epsilon, which is the ball minus a ball of radius epsilon around X. Okay, and we let epsilon tend to 0. Okay, so here we take out a small ball of radius epsilon around X, and we let d epsilon be this unit ball minus this ball around X. And then we apply Green's formula, and similar to the proof of the means value theorem, we let epsilon tend to 0, and finally we get this formula that U of X is the integral over the boundary of the ball, U of xi into minus the normal derivative of the function Gx hat, the Green's function for the ball with pole at X. Okay. So let me stop this session and start a new one. All right.
Say after a 1 minute break.
Sure, after a break. Sure, after a break. Sure, sure. Okay, so is it clear that if we use the same arguments as before with the Green's formula, we will get this formula that for any function which is harmonic in a neighborhood of the closed ball, U at X is going to be the integral over the boundary of the ball, U of xi into minus the normal derivative of Gx hat d sigma xi. Is this clear? So see, what we'll do the same thing that we did in the proof of the mean value theorem, right? So here we have this Green's formula, right? So we'll apply this Green's formula where this H is going to be the Green's function Gx hat with pole at X, and U is our harmonic function. So this integral will be 0, and then we'll get an integral over the boundary of the ball. Now that has 2 terms, but one of those terms has H in it. So that will vanish because H is 0 on the boundary of the ball. So we'll get this minus U inner product grad H with N. This is exactly U times the minus the normal derivative of the Green's function, right? The Green's function for the ball, right? And then we'll get these other 2 terms. And then as before, this H times inner product grad UN, this integral will go to 0. And this other integral will converge to minus U of P, right? By the same argument, by the same lemma from before. Is it clear?
Yes.
Okay. Yeah, so what will we get? We'll get this integral minus U of P. Yeah, so that's equal to 0. So we get U of P is equal to this integral. Okay. Do you want me to do this in detail?
It's fine.
I think it's okay. Yeah, it's the same argument as before. It's just you use that lemma that this lemma that the integral of the Green's function over a small sphere of radius r, the normal derivative of the Green's function times a function phi, this converges to minus the phi of p as r tends to 0, right? We are just using this lemma again and again. Okay. Yeah. Okay. Is this okay, Rudrada or Kujit? Is this all right?
Yeah, yeah.
It's okay. Yeah.
Yeah.
So we get this for a ball, for the unit ball in Rn, we get this Poisson representation formula for any function which is harmonic in the neighborhood of the closed ball. Okay. I mean, we can explicitly compute, we have this function gx hat explicitly, right? We have an explicit formula for it. So we can compute its normal derivative, and it turns out to be this function, 1 over Cn into 1 minus norm x squared over norm x minus xi power n. Okay. And therefore, we obtain the Poisson integral formula. U of x is 1 over Cn integral over the boundary of the unit ball, U of xi into 1 minus norm x squared over norm x minus xi power n d sigma xi. Okay. Yeah. So this function that we've got here, 1 minus norm x squared over x minus xi power n, where x is in the interior of the ball and xi is in the boundary of the ball. This is a function of two variables, x, xi. This is called the Poisson kernel of the unit ball, right? Okay. So we get the Poisson kernel of the unit ball. And if we apply the Poisson integral formula to the harmonic function u equal to constant 1, then we'll get that the integral of pxi is going to equal the value of the function u at x, which is 1. So that means the integral of the Poisson kernel is 1, right? The integral of the Poisson kernel into 1 over Cn is equal to 1. Okay. Yeah. So in fact, this 1 over Cn, I mean, this Cn is the measure of the ball, right? Of the sphere. So this d sigma divided by Cn, this is the probability measure, right? So it's saying that the integral of pxi with respect to the normalized surface area measure of the sphere is equal to 1. Okay. And moreover, by a direct computation, you can show that for each fixed xi in the boundary of the ball, the function x goes to p of xi. This is harmonic on the ball. Okay. So as a function in the first variable, the Poisson kernel is harmonic. All right. So now we've seen now that if u is harmonic in a neighborhood of the ball, then I can get it from its boundary values using this Poisson kernel, right? So this suggests a solution to the Dirichlet problem. You start with some function on the boundary f, and then take its integral with against the Poisson kernel, right? Yeah. I mean, if there is a solution to the Dirichlet problem, this Poisson integral formula tells us it has to be given by integrating with respect to the Poisson kernel, right? Yeah, this is the only possible solution there can be. So now we define the Poisson integral of a continuous function. So given a continuous function f on the boundary of the ball, you define the Poisson
What happened?
Internet issue.
Eric Kingshuk is off, right?
No, I can see him.
No, he's there, but
Yeah, I can't hear his voice.
there's no movement also from him.
Yes. Right.
Yeah, there's some
He
problem.
got this. He got disconnected.
Yeah. He'll come back, suppose.
Mhm.
Let's wait. Or Kojit.
Yes, sir.
And Utsav, both, I don't know who has this. I'm saying that this class and the previous class,
Yes.
Yes.
the recording of it, can you
Yeah, I have it.
upload or what? And
Yeah, Utsav has it. Yeah, Utsav has all the recordings. I have two. I don't have the last two lectures.
yeah, this and the previous one,
Yeah.
Okay.
because there was some disturbance. I could not listen for a few minutes.
Okay. Okay.
Okay, sir.
Okay. After the class, I'll give you the recording in. Okay. Sure.
Yeah, actually, some of the recordings Orkojit uploaded, but that's
I have
good,
uploaded. Yeah.
only
Yeah,
a
the,
few.
yeah, the recent ones.
Yeah.
Yeah, at this moment, I'm just
Okay,
saying
sir is
this and
calling.
previous
Okay.
one.
Mhm. Yeah, after the class, I'll give it to you. Yeah.
Okay. Looks like some major problem. I mean,
Yeah,
like,
sir called me. Sir is saying that his internet got disconnected.
okay, yeah.
He'll be back.
Mm.
He's trying to.
Sorry, my connection dropped. So it should be okay now. All right. So yeah.
You are.
Yeah. Okay. Right. So we've defined this Poisson integral of any continuous function on the boundary. This will be a harmonic function in the interior of the ball. Is that clear? Yeah. Just from differentiation under the integral sign, because the Poisson kernel is harmonic in X.
Yeah.
Okay. All right. So what we want to show is that, in fact, this is the solution to the Dirichlet problem for the ball, the unit ball in Rn, right? So that means we want to show that this Poisson integral, it converges to F as X converges to the boundary. Okay. Yeah. So we have to show that it extends to the boundary and the boundary value is equal to F. So that, I mean, all of you know, I'm sure, what the argument is. You want to show that as X converges to a boundary point, this Poisson kernel, it forms an approximate identity, right? And therefore, this integral converges to the value of F at the boundary point. So it's just that the Poisson kernel forms an approximate identity. So that's the statement of the next theorem is that for any continuous function F on the boundary of the unit ball, the Poisson integral extends to a continuous function on the closed ball such that restricted to the boundary, it's equal to F. Okay? And therefore, the Poisson integral is the unique solution of the Dirichlet problem. Okay? So we have to show that UF of X converges to F of Xi as X converges to Xi. All right. So given Xi in the boundary of the ball and delta positive, if I take any eta, which is in the boundary of the ball, but outside the ball of radius delta around Xi, then we can estimate the Poisson kernel at eta, right? So this is 1 minus norm x squared divided by norm x minus eta power n. But right. So so suppose x is within a ball of radius epsilon around Xi, where epsilon is less than delta by 2. Okay, so let me draw you a picture and it will be clear, the estimate. So, right. So I have a point, say xi, and I'm outside the ball of radius delta, and x is inside the ball of radius delta by 2. Okay, so my x is somewhere here. This is my xi, and my eta is somewhere here. Okay, so I have 1 minus norm x squared over norm x minus eta power n. Right. I want to estimate this now. Norm x is greater than or equal to 1 minus. So this distance is at most delta by 2. So let's say delta by 2. Okay. So 1 minus norm x squared, this is going to be less than or equal to 1 minus delta by 2 whole squared divided by, so this norm x minus eta by triangle inequality, this is greater than or equal to, well, this distance is at least delta by 2, right? Because this is in the delta by 2 ball and this is outside the delta ball. So the distance between these two is at least delta by 2. So this will be this less than delta by 2 power n. Is this okay?
Yes.
Okay. So if you choose delta small enough, then, well, okay. So let me see. What's the argument? Let me just check. Okay, so no, actually I should take epsilon much smaller than delta by 2. Yeah, I fix delta. I choose something epsilon which is much smaller. Yeah, so I don't want to delta by 2 here. I take I really want an epsilon here. Yeah. So I want an epsilon here. Oops, sorry. Wrong color. Yeah, so right, so 1 minus epsilon squared. So that's 2 epsilon plus epsilon squared. So that's less than 3 epsilon if epsilon is small. Yeah, so this is the epsilon, the estimate I want. 3 epsilon over delta by 2 power n. So if I fix a delta and then I choose epsilon very small, then this is going to be very small, right? I want to take epsilon much smaller than delta. So then if I take any sequence xn converging to xi, these functions phi n of eta is p of xn comma eta. This is going to satisfy these phi n's are non-negative. The integral of phi n into d sigma over 1 in over cn is equal to 1, right? Because the integral of the Poisson kernel is 1. And these converge to 0 uniformly on compacts in the boundary of the ball minus xi. That follows from this estimate, right? Because here, if I take any compact which is in the complement of xi, then that is contained in the sphere minus a ball of radius, a fixed delta. Okay, so delta is fixed. And then as xn converges to xi, this distance xn minus xi, which is my epsilon, that epsilon goes to 0, right? So this 3 epsilon over delta by 2 power n, this goes to 0, right? Because epsilon is going to 0, delta is fixed. So that means that this converges to 0 uniformly on compacts in the complement of xi, right? So therefore, the integral out of these functions outside any ball around xi is going to go to 0. That means it forms an approximate identity, right? Okay, so by continuity of f, this uf of xn, this is 1 over cn integral f times phi n, this converges to f of xi. Okay, these phi n's form an approximate identity. Is this okay?
Yes.
Okay, I mean, just remember the definition of approximate identity. The integral of phi n d mu is 1 over the space. So over the sphere, phi n's are non-negative. And for all delta positive, the integral over S minus the ball of radius delta around xi of phi n d mu, this goes to 0. Right? That's the definition of approximate identity. So the phi n satisfy this from this estimate, basically, right? Is this okay?
Yes.
So therefore, this function, the Poisson integral converges to the boundary value. And so we've solved the Dirichlet problem for the unit ball in Rn. Okay. All right. So now it will also be important, instead of just Laplace's equation, which is Laplacian u equal to 0, it will also be important to consider Poisson's equation, that is the inhomogeneous Laplace equation, Laplacian u equal to some function phi. Okay. So as I remarked before in the last class, that because this Green's function in Rn, g sub x, this is the fundamental solution of the Laplacian, right? So Laplacian g sub x is minus Dirac at x. Using convolution with the Green's function, right? We can solve the Poisson equation. Yes. So, so for any CC infinity function, if I take the function u of x equal to minus g0 convolved with phi, okay? So that's this function. Yeah. Then this is going to satisfy Poisson's equation. All right. Okay. So, yeah, okay, fine. So now, so this works if phi is in CC infinity. But what about a general, a more general function on the right-hand side? Okay. So what can we do then? And can we solve it for a function defined in a domain D, not on the whole of Rn? Okay. So more generally, given a bounded open set D in Rn, we can try to solve Poisson's equation, delta U equal to F in the domain D, where F is just a continuous function on D, and U is, naturally we assume U to be C2 on D. Okay. So, okay. So now we define, given a bounded open set D in Rn, and F, just an L infinity function on D. So we're not assuming any regularity, just bounded measurable on the domain D. We define the Newtonian potential of F to be the function W equal to W sub F, which is given by convolution with the Green's function. Okay. But we don't take the convolution over all of Rn. Well, we do actually, yeah. So, yeah, well, I mean, we extend F to be 0 outside the domain D. Then you can think of this integral as a convolution. Okay. So W sub x is minus the integral over the domain D, g of norm x minus y. This is just the Green's function into f of y dy. Okay. Yeah. So, I mean, that means this is a convolution if you multiply f by the indicator function of the domain D and extend it to be 0 outside the domain D, right? Then this is just a convolution. Yeah. So we will need a few lemmas which we won't prove. Okay, so this material is taken from Gilbarg and Trudinger's book, okay, on elliptic PDEs in RN. Second order elliptic PDEs. So I'm not going to prove many of the results that they do, because I mean, it's just too much material. So we're going to assume many results, okay? So the first thing to show is actually that this convolution is actually a C1 function, okay? Now, this is a bit non-trivial because, well, okay, so F is just bounded measurable, and compact support. And if G was CC infinity, then of course the convolution would become CC infinity, right? But the problem is that G is smooth, but it has a pole, right? G has a pole at this function has a pole at X, right? So it's not clear that when you convolve, you're going to get something smooth, right? Okay. So this is non-trivial. So first of all, this Newtonian potential is C1, okay? And secondly, it can be shown that if you put appropriate hypotheses on F, then this Newtonian potential is a solution of the Poisson equation in the domain D. Okay, but I'm not going to say more about this. What we will need to talk about, what becomes important in the study of these elliptic PDEs, is Holder continuous functions. Okay, so recall that if alpha is in open 0 closed 1, then a function on an open set U in Rn is Holder continuous with exponent alpha if there is a constant C positive such that norm of fx minus fy is less than or equal to C times norm x minus y power alpha. Okay. So we say that f is locally Holder continuous on a domain D if each point x in D has a neighborhood U on which f is Holder continuous, okay, with the same exponent alpha for all x in D. All right. So again, we have another lemma which we won't prove. That if f in L infinity D is locally Holder continuous on a bounded domain D, then this Newtonian potential W sub f, this is actually C2. Okay. And the Laplacian of W is equal to f. Okay, so it is a solution of Poisson's equation. Okay, so this is the hypothesis that we need, that f is locally Holder continuous. Then this Newtonian potential will give you a solution of Poisson's equation. Okay. So once we have these two lemmas, then we can get the solution of the Dirichlet problem for Poisson's equation. Okay. For the unit ball in Rn. So we have the following theorem. The Dirichlet problem for Poisson's equation on the unit ball. So let f be in L infinity of the unit ball, and let it be locally Holder continuous in the ball, and let phi be a continuous function on the boundary of the ball. Then there is a unique U which is C2 in the ball and C0 on the closure of the ball, such that Laplacian U is equal to f inside the ball and U is equal to phi on the boundary of. Okay. Right. So this is generalizing the solution of the Dirichlet problem. There f was equal to 0. Right. So there we had a solution of the homogeneous equation with a given boundary condition. Now we are getting a solution of the inhomogeneous equation with a given boundary condition. Okay. So the way to do that is the usual way. You take one solution of the inhomogeneous equation, and then you have to add an appropriate solution of the homogeneous equation, right? To get the solution, the general solution of the inhomogeneous equation, right? Yeah. So that's all you do. So your solution of the inhomogeneous equation, the Poisson equation, you take to be the Newtonian potential, right? W equal to W sub F. Then by the previous lemmas, W is C2 on the unit ball and C1 on the whole of Rn. Okay. So in particular, it's continuous on the closure of the ball. And the Laplacian of W is equal to F in the unit ball. So then we take V to be the solution of the Dirichlet problem, Laplacian V equal to 0 in the ball, and V equal to phi minus W restricted to the boundary of the ball on the boundary of the ball. Okay. So you solve this Dirichlet problem, and then to solve the original Dirichlet problem, you just take U to be W plus V. All right. Okay, so then the Laplacian of U is Laplacian W plus Laplacian V. So this is F plus 0. So this is F. And on the boundary, U is equal to W plus V. And on the boundary, V is equal to phi minus W. So the W's cancel. And so U is equal to phi on the boundary. Is this okay? Just straightforward.
Yes.
Yes.
So U is a solution of the Poisson equation, the Dirichlet problem for the Poisson equation. And for uniqueness, we just use the maximum principle, right? If U tilde is another solution, then the difference of U tilde minus U, this is harmonic because they have the same Laplacian F and they have the same boundary values. So the difference is 0 on the boundary. Therefore, the difference is identically 0. All right. Okay. Okay, so we've got a general solution to the Dirichlet problem for Poisson's equation, where the right-hand side of Poisson's equation, the hypothesis that we need is bounded and locally Holder continuous. Okay, that's the regularity we need in order to solve. Okay, bounded and locally Holder continuous. Okay, so now we're going to start talking about elliptic second order differential operators in Rn. Okay, so we already defined this, I think, when we found the coordinate expression for the Laplacian on a Riemannian manifold, right? So that will be, restricted to a coordinate chart. That will be an example of a elliptic second order differential operator in Rn. Okay, so let L be a second order differential operator on a domain D. So linear operator, of course. So then L is of the form LF equal to summation over ij, aij, del squared f del xi del xj plus sum over I, bi, del f del xi plus c times f. Okay, where f is here in C2 of the domain D. And these coefficients, a priori, we're just assuming them to be continuous. Okay, aij, bi, and c are just continuous on the domain D. Okay. So L will then map C2 functions to C0 functions. Okay, L is going to map C2 functions to C0 functions. So we say that L is elliptic if this the coefficient matrix of the second order part, this its lowest eigenvalue. So assume that this coefficient matrix is symmetric, then its lowest eigenvalue is bounded from below uniformly by a positive constant. Okay, so that means there exists a constant lambda positive such that for all vectors v equal to v1 to vn in Rn, and for all x in the domain D, sum over ij, aij of x into vi vj is greater than or equal to lambda times norm v squared. Okay, so this is the ellipticity condition. Okay, so you see, studying the Dirichlet problem for the Laplacian on a Riemannian manifold, when you look in coordinates, the Laplacian is going to become a second order elliptic differential operator, right? Because we saw that the coefficient matrix for the Laplacian was G upper ij, right? Which was the inverse of the matrix of the Riemannian metric, right? So on a compact domain, that's going to be elliptic, right? On a compact domain in my Riemannian manifold, it's going to be elliptic. Okay. So naturally, we then want to study the Dirichlet problem for a general operator L in Rn. Okay. So what we want is the following. We want to solve the Dirichlet problem for the inhomogeneous equation. So given f a continuous function on the domain D and phi a continuous function on the boundary of D, we want to find u, which is in C2 of D, intersect C0 of D closure. So C2 in the domain and continuous on the closure, such that Lu is equal to f in D and u is equal to phi on boundary D. Okay. So we've already done this when the domain D is equal to the unit ball and the operator L is equal to the Euclidean Laplacian, right?
Right.
Then we've solved this problem. We just need to assume that this function f is bounded and locally Holder continuous. That's the assumption that we need on f. So we're going to solve this general problem again for the unit ball via what's called the method of continuity. And this will involve considering the operator L as a perturbation of the Euclidean Laplacian. So that means you look at the one parameter, you look at the operators LT, which is just a convex combination of the Euclidean Laplacian and the operator L. Okay, so this is 1 minus T L naught plus TL, where L naught is the Euclidean Laplacian, summation del squared del xi squared. Okay. And the method of continuity, to finish with, I'll just say it's this result. It's a result from functional analysis. So, okay, we've just got 2 minutes left. Let me not rush things. We'll talk about this next week. So, yeah, so we're going to use a soft method from functional analysis. So where basically, if you know a solution for L naught for the Euclidean Laplacian, you will also get a solution for all of these operators LT. Okay. That's the idea. So yeah, I'll describe this next time. We'll talk about this next time. So any questions? Okay, so that's why we solved the problem for the Euclidean Laplacian on the unit ball first, because we're going to use this method of continuity. So we need to know that basically the method will say that if a solution exists for L naught, then it will also exist for all the operators LT. Okay. Under some hypothesis on the operators LT. Okay. That's the idea. Okay, then. So if there are no questions, let's stop today and I'll see you next week.